So welcome to lecture 31 on Riemannian symmetric space. So I begin with a small proposition. So let G be a connected Lie group with Lie algebra G. So let sigma 1 comma theta 2 be from G to H be 2. So Lie group homomorphism. So that d sigma 1 is equal to d sigma 2. So then sigma 1 is equal to sigma 2. Okay. So it says that if G is a connected Lie group and there are two Lie group homomorphisms so that its derivatives are same, then the two group homomorphisms will coincide. And connectedness is a very useful connectedness is an important assumption here. So proof is very simple. You look at this thing, sigma 1 of exponential of x. So that is really exponential of d sigma 1x. Okay. And this since d sigma 1x is equal to d sigma 2. So you can write this as exponential of d sigma 2x. And exponential of d sigma 2x, this is equal to sigma 2 exponential x. And this happens for any x belongs to G. Okay, since G is connected, this thing, you know that this exponential of x, so that x belongs to G, this generates G. Therefore, sigma 1G is equal to really sigma 2G for all G belongs to G. So this is the thing. So just wait 1 second, I will close the door. Okay. So now I want to really little bit of discussion. So small discussion. So let phi from G to H be a Lie group homomorphism. Then I have told you then this phi G is a Lie subgroup of H with Lie algebra of phi G is really d phi G. But what is d phi G? D phi G is real where G is equal to Lie algebra of G. So one thing I have to, you know that this Lie algebra of a group and Lie algebra of a connected component of identity of that group are same. So therefore, so Lie algebra of phi G naught, okay, where G naught is the phi G naught is the connected component of identity. This is called Lie algebra of phi G. This is same thing as a d phi G. Okay. Okay. Similarly, this phi G naught is the connected component of identity inside G, is a Lie subgroup of H with Lie algebra of phi G naught is equal to d phi this Lie algebra of G naught, and Lie algebra of D naught is really Lie algebra of G. This is equal to d phi G. Now both this phi g naught and phi g naught are connected Lie subgroup of H with same Lie algebra d phi g. So I have told you that if two connected Lie subgroups have same Lie algebra, then they are same actually. They, hence by uniqueness, this thing is happens. Phi g naught is equal to phi g naught. Actually, this is a useful piece of information. We have used this information in the previous lecture. Actually, in this thing, when I have told you that Rg of H naught is equal to Rg H naught. Okay, here instead of phi, you can take Rg. Okay, so to proving this, actually you can use that fact. Okay, so this is the thing. Now discussion. Okay, so let G be a Lie group which acts smoothly on M. Okay, and the action is not necessarily transitive. Okay, so I am not assuming action is not necessarily transitive. Okay. So now the thing is, therefore, let phi from G to this symmetry group of M be the corresponding group of homomorphism. Actually, since this action is smooth, actually instead of symmetry group of M, you can replace by this diffeomorphism of M. So this is you can replace by diffeomorphism of M. Okay. So this is diffeomorphisms of M. Okay. So you understand what this means. So let N is equal to really this kernel of phi. Kernel of phi, what is this? This is really G belongs to G. So that G dot M is equal to M for all N belongs to N. Okay. This N is called ineffective kernel. Ineffective kernel. Ineffective kernel or unfaithful kernel, right? Or unfaithful kernel. Now we say that okay, so now this N is by definition this is a closed subgroup of G. So hence by Cartan's theorem it is a Lie subgroup of G. Okay, so clearly N is a closed normal. Yes, closed. Clearly N is a closed normal Lie subgroup of G. Therefore, Lie algebra of N is an ideal in G. This is okay. Now we say that recall. Okay, we say that this thing G acts on M effectively or faithfully if and only if this N is equal to identity. Okay, now I want to give a definition. So let us, oh God, I really left this place somehow. Sorry.
You can cut and paste.
No, actually, I do not know much. Okay, let us say that that's okay. That space is fine. So definition. We say that okay, this is important definition. G acts on M almost effectively if and only if this N is discrete. Okay. So if N is discrete, then we say that this G acts on M almost effectively. And we can also, this is equivalent to the fact if and only if Lie algebra for N is equal to 0. So now, so this is the thing. Now one example I want to just give you. So you remember this thread, G acts on M almost effectively if and only N is discrete, if and only if Lie algebra for N is equal to 0. Okay, so now one example. So let G be a connected Lie group. Okay. Then and let H be a okay Lie group with Lie algebra of G is really G, and let H be a Lie subgroup of G with Lie algebra of H is really small h. Then this H acts on G, acts on this Lie algebra G via adjoint representation. And okay, acts on G linearly. Okay, let us write this. I will explain what is the that linearly. On G linearly via adjoint representation. And the action is given by this thing h dot x, simply this thing add G h of x. This is h belongs to h and x belongs to G. The action is linear means what? This if you look at this thing, fix an h. If you look at this x going to this map h dot x, this is a linear map. Okay, for fixed h. So that is meaning of the action is linear. Okay. Now in this case, the corresponding the corresponding group homomorphism is what? Is really this is the thing. RG. This is the map. RJ to GLG. Okay. We have seen that in previous lecture. We have seen that this thing kernel of RG. This is actually RG restricted to H. Kernel of RG H is equal to H intersection ZG and G mod of and H mod H intersection ZG is isomorphic to RGH. We have shown that this is an isomorphism. Okay. In the previous lecture, we have proved this fact. And one thing I must tell that in that proof, we have assumed that both G and H are connected. But to prove these two facts, you do not need that H is connected. The fact H is connected is used to prove something else. Okay? So what I'm saying that to prove these two things, you do not need H is connected, but you need G is connected, and I have assumed that. Okay, so this kernel of this this um, group homomorphism RG is really H intersection ZG, and this is the unity kernel. So hence H intersection ZG is the ineffective kernel for the H action. Okay, hence H acts on G effectively if and only if H intersection G is ZG is real. Similarly, Similarly, H acts on G almost effectively if and only if this H intersection ZG is equal to H intersection ZG is discrete. This is equivalent to the condition that so if and only if this is equivalent to the condition if and only if this H intersection ZG is equal to 0. Okay. Now, okay, so this is the thing. So actually I am leaving many places. Okay, so H acts on G almost effectively if and only if this H intersection ZG is discrete. And if and only if H intersection ZG is equal to 0. Suppose so H acts on G effectively and RGH is compact. Then what do you get? Then we have this thing RGH is equal to H intersection. This is isomorphic to ZG intersection H. This is isomorphic to H because ZG intersection H is equal to E. So this is real isomorphic to H. Hence, in this case, H is compact. Okay, so that is the thing. Now, okay, proposition. So let us see one proposition. Let M be a RSS and G is equal to really isometry group of M. So let P belongs to M and K is equal to stabilizer of P inside G. So then G acts on M effectively and ZG intersection K is trivial. Okay. So as I have said, this fact implies is equivalent to the fact that K acts on G effectively. And this thing will also imply that this thing ZG intersection K is equal to 0. Okay. So let us see. So proof is very simple because since see the thing is G acts on M and G consists of functions on M. Okay, and the action will be always transitive in this situation. Okay, so let me do the proof, then I will tell you what I am saying. So let G belongs to G. Suppose G dot M is equal to M for all m belongs to m. This implies G of m is equal to m for all m belongs to m. Therefore, G is identity. This is as trivial as that, as this. So G is equal to identity. Now let G belongs to ZG intersection K. Now then you can apply G on you can apply on H dot P. So this is really GH dot P, but G belongs to ZG, so GH is equal to really HG dot P. Then you can really write this thing H of G dot P. But G dot P, since G is also in the stabilizer, G dot P is equal to this is equal to H dot P. Okay. So now this gives me G of H dot P is equal to H dot P. Now H is arbitrary, H belongs to G. Now as G acts on G acts on M transitively. So this implies G is equal to identity. Okay. Now I recall the definition of Riemannian symmetric pair. What was the definition? Let G be a connected Lie group. And H be a closed subgroup of G. The pair G comma S is said to be a Riemannian symmetric pair if there exists an involutive automorphism sigma from G to G, so that this thing happens. First thing is G sigma naught inside H, so subset of G sigma. Second thing is RGH is compact, right? Now for the timing, you just forget this second condition. Okay, so using this thing, okay. So what did you? So just concentrate on the first condition. Okay, so what you do? So let theta is equal to real D sigma, and G is equal to really Lie algebra of G. Then we have seen that this theta is a theta. Then theta is automorphism of G, and theta square is equal to identity, and theta is not equal to identity. That is, theta is an involutive automorphism of G. Second thing is I have really we have seen this thing K is equal to really X belongs to G, so that theta X is equal to X, and P is equal to X belongs to G, so that theta X is equal to minus A. Since this theta is an involutive automorphism, so this is not equal to 0, and this K is equal to actually Lie algebra of K, and we have got this thing G is equal to K plus P. This was our cut-and decomposition. This was our cut-and decomposition. This much we have got from the condition 1. Okay. Okay. Now the second condition. What does this second condition imply? So the second condition, if you have followed my last lecture, the second condition will imply that this Lie algebra of H. So this will imply that K is compactly embedded in G. Okay. Now if K is K is compactly this Lie algebra K is not Lie algebra of K. This is Lie algebra of H. This is compactly embedded in G. And if H is connected, these two conditions are equivalent. K is compactly embedded in G, implies that RG is compact. This, if H is connected, this happens. Now I am ready to give the definition of orthogonal symmetric Lie algebra. So now definition. A pair G theta is called an orthogonal symmetric Lie algebra, and I will use this acronym OSL. OSL stands for orthogonal symmetric Lie algebra. If first thing is G is a Lie algebra over R. Second thing is theta is an involutive automorphism of G. And third thing is this K is equal to X belongs to G, so that theta X is equal to X. This is a compactly embedded subalgebra in G. Subalgebra in G. Actually, Helgason and that note use this notation instead of K, they use this notation U. So what I'm saying that if you look at fixed points of theta, that is a compactly embedded subalgebra in G. Okay. Now, so definition. An orthogonal, so let G theta be an OSL as above. So then the OSL G theta is called an effective orthogonal symmetric Lie algebra. Lie algebra. Okay. I will use this acronym OEOSL, effective orthogonal symmetric Lie algebra. Effective orthogonal symmetric Lie algebra. If and only if this ZG intersection U is 0. This is the thing. Okay. Now, okay, so first example, let us give. Okay, so before example, suppose let G theta be an orthogonal symmetric Lie algebra. Tapendo, is it clear so far?
Yeah. So involutive automorphism means theta square is identity and theta not equal identity, right?
Yeah. So this means theta belongs to automorphism of G. Theta is not equal to identity, and theta square is equal to identity. Okay, so where was I? Okay. So let J theta be in an OSL. So let U is equal to this is, you can write a discussion. Okay, so let U is equal to really X belongs to G, so that theta X is equal to X. This is the +1 eigenspace, right? And E is equal to really X belongs to G, so that theta X is equal to -X, and this is -1 eigenspace. So and E not equal to 0 because okay. Now this thing G is equal to U plus E, direct sum. This is direct sum. And this is called Cartan decomposition. Now, what is this thing? Okay, now x, if x belongs to G, this then you can write x plus theta x by 2 plus s minus theta x by 2. This will belong to U and this belongs to E. And another thing is, if you look at this thing U, this is a plus one eigenspace. This is a plus one eigenspace. So this is really, it belongs to plus one eigenspace. So this is plus one, therefore plus one. Use that theta is an automorphism of G to prove this thing. Actually, I have proved this in the context of Riemannian symmetric. You can prove it here also. This is now this thing U E is really E, and E is equal to U. This is really plus one, minus one, minus one, minus one, minus one, plus one. Okay, so hence what you get, hence this U is a Lie subalgebra of C. But E is not a Lie subalgebra. Okay. 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 Now, now we come back to the thing is one example and what. So this example actually I have discussed this thing, but we will give later on more examples. So let GH be a Riemannian symmetric pair. Then I have told you that, okay, with involution say sigma from G to G. Then this thing, then G, okay, and let theta is equal to, sorry, what I am writing, with involution sigma from G to G. So let G is equal to really Lie algebra of G, and K is equal to Lie algebra of H, and theta, okay, and theta is equal to real D sigma. Then G theta is an orthogonal symmetric algebra and associated to this thing, to the Riemannian symmetric pair GH. Now definition, this is a so the Riemannian symmetric pair GH is said to be effective if the corresponding OSL, this thing G theta, okay, where G is this and theta is equal to D sigma, is effective. Now hence the pair the RSP GH is effective if and only if this thing happens, ZG intersection K is equal to 0, where K is Lie algebra of H. This K is Lie algebra of H. So this happens if and only ZG intersection H is discrete. Okay. This is equivalent to the fact RG H action on G is almost equative. So warning. The Riemannian symmetric pair G is effective does not mean or imply by that G acts on G mod S effectively on G mod S effectively or almost effectively. It simply means this thing which I told you. It simply means H acts on G or RG acts H G is almost effective. These are two things. Actually, people should. It would have been the better if people would have called this condition JG intersection K is almost effective, but they have called it effective. Okay. Oh God. Okay. Okay. So this is the thing. Now we want to prove some interesting things, and we will go to classification. So proposition. So let G comma theta be an OSL. So first thing is with G is equal to U plus E. Whenever I will write this G is equal to U plus E, you must understand that this is really cut-and decomposition. I am writing this is cut-and decomposition, and the standard notation is the you take U for plus one eigenspace and E for minus one eigenspace. Okay, so first part is this U is orthogonal to E with respect to the Killing form BG. So second thing is B, suppose this G theta is effective, then this Killing form BG restricted to U cross U is negative definite. So this notation precisely means this is negative definite. This means this thing BG restricted to U cross U is negative definite. 2 less than equal to symbols. Okay. Similarly, 2 greater than equal to symbols is means positive definite. So I am using those things. Okay, proof is very simple. So proof of A. Okay. So let X belongs to E and X belongs to U and Y belongs to E. Since theta belongs to this automorphism of G, so this B of theta BG of theta X theta Y is equal to BG of XY. I have proved this proposition last time. So this will imply that BG theta X belongs to U. So theta X is equal to X and Y belongs to U. This is minus Y. So BG XY. So hence I will get? I will get something like this. Minus of BG XY is equal to really BG XY. This implies BG XY is equal to 0. Hence this U is orthogonal to E with respect to BG. So now B, what is the B? Suppose d theta is effective. Okay, So by definition of orthogonal symmetric Lie algebra, U is compactly, since by definition of orthogonal symmetric Lie algebra, U is compactly embedded in Z. And this is effective. That means ZG intersection U is equal to 0. By one of our, we have proved this thing, one of our previous proposition. This thing BZ U cross U is negative definite. This is clear. Okay. Okay, so let us. So we have proved this thing. So now I want to give an important definition. So pay some attention here. Definition. Let G theta. Okay. An effective orthogonal symmetric Lie algebra G theta is said to be of first thing Euclidean type. If this happens, you look at always BG restricted to U cross U negative definite. So there is an part E which is, so if BG restricted to E cross E is identically 0, then we will say that the effective orthogonal symmetric Lie algebra G theta is said to be of Euclidean type. Now second thing is compact type.
Muna, what is the reason it is called Euclidean type?
Actually curvature will be 0 and it will be, if simply connected, it will be diffeomorphic to Rn.
Curvature of what?
Sectional curvature
Curvature
will
of
be 0. The manifold, I will define using orthogonal symmetric Lie algebra, whether this is Euclidean type and compact type or non-compact type. So we will define define whether the Riemannian symmetric space is of compact or non-compact or Euclidean type. It turns out that if the Riemannian symmetric space is of Euclidean type, then sectional curvature will be 0. And if that is simply connected, that is diffeomorphic to your Rn. So, okay, I will go slowly those things. This will come here. Compact type. Oh, if so, after so many days, I am hearing you, right?
Yeah.
Okay. So non-compact type. If BG. Okay, this is means BG restricted to U cross E is negative definite. BG restricted to E cross E is positive definite. Sometimes people call this as a type 0. Type 0 means sectional curvature is identical 0. We will not have time to do this thing, but let's see. So this is a real type plus. The sectional curvature is really greater than equal to 0, and but it is not identical. It will not be identical. So similarly, type minus. This is really sectional curvature is less than equal to 0, and but it will be not identical. These are the thing. Okay, so these are the very important thing definition. In effective orthogonal symmetric Lie algebra G theta, it should be Euclidean type. To E cross E is negative definite, and if non-compact type, if BG restricted to E cross E is positive definite. This means positive definite. Okay, so remember this notation. This means positive definite. Okay, so we will give some equivalent characterization of this Euclidean and compact type. So let me do that. So first proposition, So let G theta be an effective orthogonal symmetric Lie algebra. Then G theta is of Euclidean type if and only if this thing EE, the Lie bracket of EE is equal to 0. Okay. So proof is suppose so G theta is of Euclidean type. That means what BG XY BG restricted to E cross E is identically real, right? This is the thing. Okay. Now what I have to prove that Lie bracket of EE is equal to 0. So let this X belongs to E, Y belongs to E. Then this XY. Okay, so this is okay. This will belongs to EU because I am using this fact that EE Lie bracket of EE is equal to inside EU. Since this thing. Okay. So let Z belongs to U. Now I took a look at this BG XY Z, and this is same thing at BG X Y Z. And this is the I have proved this. This is the fact that killing form is associative. So this is as BG is associative. Okay? I have proved this. Now this Y belongs to E. Okay, so let us see. This Y belongs to E, and this Z belongs to U. So this implies whole thing is in E, and this X is in E. And since BG restricted to E cross E is equal to 0, so this is equal to 0. Okay. Now this happens for any Z belongs to U. Okay. So now as BG restricted to U cross U is negative definite, therefore, and this XY Lie bracket of XY belongs to U, therefore this XY is equal to 0. Okay. Hence this thing E is 0. So this is the thing. Now let us use a phase space. Okay, this part is clear. Conversely, suppose this thing EE is 0. Okay. Now the thing is this will imply that well, okay, so what I have to show that BG XY of BG on E cross restricted to E cross E is equal to 0. So let X belongs to E, Y belongs to E, and okay, fix this thing. Fix X belongs to E and Y belongs to E. Let Z is equal to really Z1 plus Z2, and this belongs to G. This is Z1. You assume that this belongs to U and this belongs to E. This is the corresponding cartographic computation. Now you look at this thing RGX, RGY, Z1. This is really X, Lie bracket of Y, Z1, and Y is where? This Y is in E. Okay, so this let us write. This is in E, and Z1 is in U. So whole thing is in U, E, and this X is in E. So and Lie bracket of E is equal to 0. So this is 0. Now similarly RG X, RGY, Z2 is really X, Lie bracket of y z2. Okay. This is really y is in where? E. Z2 is in where? E. Okay, and we have really seen that Lie bracket of E and E is 0, so this factor is 0. So this will be 0. Okay. Hence, we will get what? RGX, RGY. This is equal to identically 0. Okay, hence this is equal to 0, Z is equal to 0. This implies RGX, RGY is equal to 0. Therefore, hence this BG XY, this is a trace of RGX, RGY, this will be 0. Therefore, BG restricted to E cross E is identical. So this was the thing. Now I want to give one more proposition. So let G theta be an effective orthogonal symmetric algebra. Then G theta is of compact type if and only if this BG is negative definite. This proof, okay, sorry. Let us, okay, so let us use a phrase space then. Statement is here. Okay. So suppose this BG is negative definite. This will clearly imply that BG restricted to E cross E also negative definite. This implies G theta is of compact. This one-sided is clear. Okay. Suppose G theta is of compact type, then this thing happens. BG restricted to E cross E is negative definite. Okay. Now, okay, we already know that since this is an effective orthogonal symmetric Lie algebra, we already know that this thing BG restricted to U cross U is negative definite. So let Z is equal to, okay, let 0 not equal to J. This is equal to Z1, Z2 belongs to G. Okay. Now this Z1 belongs to U, Z2 belongs to E. Then this thing B of ZZ. Okay, so this is really B of Z1 plus Z2 and Z1 plus Z2. So this is really B of Z1 Z2 plus, sorry, not Z1 Z2, B of Z1 Z1 plus B of Z2 Z2. And other things will be 0 because, as I said, that U is orthogonal to E. This implies B, okay, as I should write this BG Z1 Z2 is equal to 0 because this Z1 belongs to U and this belongs to E, and U is orthogonal to E with respect to killing power. Okay, so therefore we will get this thing, and since 0 is not equal to Z, this both either one Z1 or Z2 will not be 0, so this is strictly less than 0. Hence BG is, okay, hence BG is negative definite. Okay. Okay, so this proves this thing. Now corollary. Let G theta be an effective orthogonal symmetric Lie algebra of compact type, then G is semi-simple because the killing form will be definitely non-degenerate. Okay. So now I want to give a definition.
This is because it is negative definite both on U and E, right?
Oh. So this killing form is negative definite. Whole compact Lie
Yeah.
algebra, it is negative definite.
Yeah, that's what I'm saying.
Because of U and E, but you have to really, I am using also this fact that U and E are orthogonal with respect to the killing form. That
Okay,
fact is used.
okay.
Otherwise, that would not be true.
Okay.
Ustab, is it clear? Hello, Ustab? No, he is not there. Is he? Anway, whatever.
Yeah, it's clear.
So definition ZGBA Lie algebra over K. This K is either R or C. Okay. Then we define this thing radical of BG killing form. This is okay. So this is equal to X belongs to G. So that BG XY is equal to 0 for all Y belongs to G. This is called radical of killing form. Okay. Now, yeah. So hence, G is semi-simple if and only if radical of BG is 0. This thing is trivial. So now I want to prove the proposition for the non-compact case. So let G theta be an effective orthogonal symmetric Lie algebra and of non-compact type. Then G is semi-simple. So here in the compact case, you are saying that always the scaling form is negative definite, but here these are two parts. One is negative and other positive definite. On U it is negative definite, on E is positive. But the Lie
So
algebra will be same.
For Euclidean type, it cannot be semi-simple, right?
For Euclidean type, it will not be semi-simple. Yes.
It will not be semi-simple.
Yes. Because whatever, if you take this X belongs to E, then BGXY is equal to 0 for all Y belongs to Z. It will not be semi-simple for all Y belongs to G. Because
So
BG.
so it's a question out of curiosity. So can you say that it would be solvable or nilpotent, something like that, or it will be mixed type for Euclidean case?
Euclidean case, G will be solvable.
Yes. Or see, one part will be abelian. That E part is abelian, right?
Okay, so X, Y. This will be solvable, I think. So this, see the thing, X. No. At this moment, I am not sure. I will tell you.
Okay.
But it seems that it is solvable because. Okay, I will answer this question.
Yeah.
So proof is, so let z is equal to really z1 plus z2. This belongs to radical of bg. Radical of this killing point. This will belongs to u. This belongs to e. So then this. So as this is radical, this is z belongs to radical of bg. So bg z x will be 0 for all x belongs to u. Now that will give you bg z1 plus z2 x is equal to 0 for all x belongs to u. Now this is belongs to u and this belongs to e, and I use this fact that u is orthogonal to e. So from that fact you will get this bg z1 x is equal to 0 for all x belongs to u. Now as bg restricted to u cross u is negative definite, this will imply that z1 is equal to 0. Hence, think z will be z2. Right? Now, as z belongs to radical of bg, so this will imply that b of z y is equal to 0 for all y belongs to e. Now b, this is really z2, y is equal to 0 for all y belongs to e. So this both are belonging to e. This belongs to e. This will imply that b of okay. Now as this thing b g restricted to e cross e is negative positive definite. This implies z2 is equal to 0. Hence z is equal to 0 and thus g is semi-simple. So I will combine both the proposition. So hence we for compact and non-compact type. So I will write. So hence we get the following proposition. So this proposition is something like this. Let g theta be an effective orthogonal symmetric Lie algebra and which is either of compact or non-compact type. Okay, so then G is semi-simple. So we have proved this thing. So now I want to give a definition. So an effective Riemannian symmetric pair G theta G mass is said to be of type mu, where mu is belongs to set compact, non-compact, or Euclidean. Euclidean. If and only the corresponding effective orthogonal symmetric Lie algebra G theta is of type mu. So now the thing. So if the Riemannian symmetric pair GH is of, if the corresponding orthogonal symmetric Lie algebra is of non-compact type, then the Riemannian symmetric pair is also, we will say that this is of non-compact type. So it is also clear that if GH with the effective Riemannian symmetric pair, GH is of compact or non-compact type, then G is semi-simple. So I will prove a very important proposition. Like actually, I will before.
Muna,
Yes.
so you are adding an extra term to that Riemannian symmetric pair that is effective, right?
Yes.
And then there are three classes of these things. So are there symmetric spaces outside these classes?
Yes. You can
Okay.
take the product of you will get this thing. For instance, GL this thing.
Okay,
Okay,
you can take
I
product of one Euclidean and no one.
to other thing. We will see. We will see some examples. We will see a lot of examples. Okay, proposition. Okay, so let G comma H be an effective Riemannian symmetric pair with involution sigma 1 from G to G. This is the involution. Suppose sigma 2 from G to G be another involutive automorphism of G, so that following thing happens, so that so G of sigma 2 not inside H, G of sigma 2. Okay, I was right. Okay, this was the notation. Okay. G of sigma 2. So then sigma 1 is equal to sigma 2. So look at the statement very carefully. Let G comma H be an effective Riemannian symmetric pair with involution sigma 1 from G to G. So that suppose sigma 2 from G to G be another involutive automorphism of G, so that G of sigma 2 naught is subset of H, subset of G of sigma 2, then G sigma 1 is equal to sigma 2. It says that this for an effective Riemannian symmetric pair, this corresponding involution is unique. Okay, and what is the condition you want to take? This effective. And we have seen that if a Riemannian symmetric pair which comes out of a Riemannian symmetric space, that is always effective. So this is a natural condition to take. Okay, and ideally one thing, actually whenever one defines this Riemannian symmetric pair, one should take this like G comma H comma sigma, where sigma is the involution, but people write G comma H because of this proposition. Because of since this for effective Riemannian symmetric pair, there is just a unique involution. For that reason, we do not write that G comma H sigma. Okay. Now proof is let okay, so let theta 1 is equal to D sigma 1 and theta 2 is equal to D sigma 2. So then this G is equal to, we will get this K1 plus P1 and G is equal to K2 plus P2. Okay, this is the K1 plus P1 is the cut and decomposition with respect to theta 1. theta 1, and this is really Cartan decomposition with respect to theta 2, right? Okay. Now the thing is, what is K1 here? K1 is the Lie algebra of H. Right? K2 is also Lie algebra of H. So both K1 and K2 are same. So I write those things for K. Okay. So now, so let X belongs to P1. I use the second Cartan decomposition. This implies X is equal to some Y plus Z. This Y belongs to where? This K, and Z belongs to P2. And X, remember, this is in P1. So this Y is equal to really X minus Z, and this is belongs to P1, and this belongs to P2, and this whole thing belongs to K. Right? Now, okay. So this Riemannian symmetric pair is effective. So that means as okay. So let us see. Let us first find this BG of Y comma Y and this thing. Then I really write this Y, and one Y I really put this X minus Z. So I will get this thing BG YX minus BG YZ, right? So this Y belongs to where? K, and this is really P1. K is orthogonal to P1. Similarly, this K is orthogonal to P2 with respect to killing power. So K is orthogonal to P1 and K is orthogonal to P2. P1 and K is orthogonal to P2. So this is equal to 0. Now as okay, this thing BG restricted to this thing. Okay, as this as GH is effective, you get something like this thing. ZG intersection K is equal to 0. Hence, this thing BG restricted to K cross K is negative definite. Now, as Y belongs to K and BG really YY is equal to 0, then therefore this implies Y is equal to 0 since BG is negative definite. Thus, what we'll get this X is equal to Y is equal to 0, so X is equal to Z, and this is belongs to P2. Hence, we get this P1 is subset of P2. Now I can by changing the role of P1 and P2. P2, I get we get this P2 really P2 is P1. Now thus what we get P1 is equal to P2. Now what is theta? Theta is theta 1. Theta 1 is equal to really, if you look at this thing, theta 1 is identity on K plus minus identity on P1, right? But P1 is really P2, so I can write this identity on K plus minus identity on P2. And this is some same thing as theta 2. So hence theta 1 is equal to theta 2. This implies d sigma 1 is equal to d sigma 2. Now, as G is connected, we have proved this first proposition. If derivatives are equal, then therefore this sigma 1 is equal to 0. So this finishes the proof. Is it clear, Manali?
Yes. Yes, it is
Okay.
clear.
Okay, is it clear? Okay. Now I want to give another definition. Okay. So let M be a Riemannian symmetric space and G is equal to IM naught. So let P belongs to M and this K is equal to really stabilizer of G inside P. Then we have seen that what I have said that we have seen that this G comma K is an effective Riemannian symmetric pair. We have proved that proposition that ZG intersection K is equal to 0. It is much more than that. So M is called a RSS of type mu, Riemannian symmetric space of type mu, if and only if the corresponding Riemannian symmetric pair GK, and this is effective. Okay. Riemannian symmetric. Okay. Let us write the effective Riemannian symmetric pair G comma K is of type mu. Okay. So now the thing is where what is mu? Mu is either is compact, okay, non-compact or Euclidean. Actually, I have mu belongs to, and I should write this mu type. So type mu. Now last thing, I will then stop. Okay. So little discussion. So let G1 H1 be a Riemannian symmetric pair with involution sigma 1, and let G2 H2 be a Riemannian symmetric pair with involution sigma 2. Then this check that this thing G1 cross G2 H1 cross H2 is a Riemannian symmetric pair with involution defined by thing sigma from G1 cross G2 to G1 cross G2 given by sigma of G1 G2 is equal to sigma 1 of G1 and sigma 2 of G2. Moreover, if G1 comma H1 is an effective Riemannian symmetric pair, and G2 comma H2 is an effective Riemannian symmetric pair, then this thing G1 cross G2 H1 cross H2 is also an effective symmetric. Riemannian symmetric pair. Okay, and suppose G1 comma H1 and G2 comma H2 are effective Riemannian symmetric pair of type say mu, of same type mu, say when there are Riemannian symmetric pair of same type, okay, of same type mu, Then G1, G2, H1 cross H2 are effective Riemannian symmetric pair of type mu. The product will retain the same type, and everything. These are simple exercise. If you think for 1-2 minutes, then you can do everything. I am putting everything as exercise, and with this I would like to stop, and if there are questions you can ask me, and in the next lecture what we will do, we will see some examples and we will really prove many things there. So if there are any question you can ask me, Manoj da or Sanjay da, Mithun da.
No, it's okay. Thank you.
Muna.
Yes. Rajesh da, I am stopping. I am leaving then.
Okay, and now I'm stopping this recording.